Hey, Théau, thank you for coming in and doing this interview. I mean, your work is marvelous. You've got such a great history of accomplishment, even as a teenager, winning grand prizes for physics and things like that. So, a lot of development. You even have an advisor now in your company who has a Nobel Prize in quantum, right? So, you're in a really good place, and fault tolerance is where it's at, and you're one of the leaders in the world at fault tolerance. But it's a race, right? So let's mine some of this. And again, thank you, Theo, for coming in.
Thanks, Stephen, for having me. It's always a pleasure.
So Theo, if you can give me maybe two or three milestones early in your life, and it could have been when you're 3 or 5 years old, inside, outside school, outside your family that really shaped you to who you are today. And including, for example, when you were in secondary school, you gravitated towards physics and electronics and competing in the International Young Physicist Tournament. I mean, that's pretty phenomenal. But what drove you to that? Or, you studied quantum physics, both for your master's and or physics and then quantum physics and then for your PhD. Well, what drove you to that? And what drove you to be an entrepreneur? I mean, was there something when you were 10 years old that kind of got you in this path? It sounds like you were good at school, but maybe not initially. Who knows? So I want you to define three pivotal moments that made you this continuing enormous success you are today.
Yeah, I mean, I don't know about the success. It's a bit early, but we're definitely on a good path. I think so. You mentioned one of those pivotal moments. Indeed, I had. I mean, I've always been good in science at school, but I had, life is about serendipity, and so I had the chance in high school to meet a young researcher, Nicolas Chevalier, who was looking for a high schooler to partake in a global tournament about physics. And I said, well, you know what? Why not? I'm gonna dedicate all my Saturday mornings and early afternoons being in a lab with a few friends and starting to play around with physics. And this is where I really, discovered the what is the job of a physicist? Not the way you learn it at school, but actually what does it mean to try to answer an open question? Like, why are the edges of coffee stain darker than the middle of it? Which is a quite open physics problem. And so you spend your whole year preparing about 17 of those open problems, and then you meet with other teenagers and you do what are called physics fights. It's really debating around physics in a sort of tournament with rules, but that really gets to the essence of what it means to be a physicist. It's about pursuing science, but eventually trying to convince your peers. And so when you write a paper, a scientific paper, the reason why it's a paper, it's because you're trying to convince others that you're bringing a new look, a fresh look to an open, existing, or interesting problem. And so I really fell in love with the way with the job of a physicist at that point. In high school, I also had another academic or serious passion, which was low-level electronics. How do you assemble transistors to make early logic functions? But pretty quickly, I realized I was coming 40 years, 50 years too late to make any meaningful contribution. Too many very smart people were there before me. So I focused on physics. And then a second pivotal moment I remember actually, it was in 2012 when I entered École Polytechnique. It was exactly at the time where Serge Haroche and David Wineland got their Nobel Prize for manipulating individual photons or ions. And I remember thinking, telling myself that this kind of physics is so cool because it's the kind of experiment that only requires a few physicists. It's a reasonable scale experiment, and yet you get to play with the foundation of quantum mechanics. and you get to do experiments that used to be thought experiment to try to think of the weirdness of quantum mechanics here at a very reasonable scale. And at the same time, I read an IEEE spectrum paper or article, whatever, about the promise of a quantum computer. And so the two collided in late 2012 in my head, saying, well, it's a match made in heaven for me to combine both my passion for physics and low-level electronics, because this is a brand new playground where you get to rebuild a computer from the ground up. At the same time, playing around with the foundation of quantum mechanics, and yet there is so much room to be clever and bring new ideas, patterns in this race. And maybe the last one was in 2015 during my first master internship, where I got to meet with Benjamin Huard, who will eventually be my PhD advisor, and his group, the quantum electronics group, that was actually started by Michel Devoret, the other Nobel Prize of this year. And here I not only fell in love with this kind of ways of building a quantum computer using superconducting circuits, but also with the people. And that group of researchers was so welcoming, so brilliant, and yet very humble, that I just didn't want to leave afterwards, you know. And the reason I became an entrepreneur eventually was really because of two things. The first is that I come from a personal or familial background that is not really about science, rather about business. So at home we discuss more about board of directors discussions than about physics. And the second reason is because I just wanted to keep on working with those researchers and scaling their efforts, scaling them in some sense. And so this is how we started Alice and Bob, because we had an angle, but most importantly, we had a brilliant team already functioning as a startup despite being in academia at the time. And this is how we got started so rapidly. So I'd say those would be my three main milestones that made Alice and Bob and my early career in physics possible.
Okay, so what I'm hearing is you grew up in an enriched environment that was kind of more business centric, board of directors, annual repeat revenue, how do you keep expenses down, grow the business, manage the people, continue to innovate and things like that. But you also had a propensity when you were really young for things like electronics and physics and math and science, and that's we were fortunate to get into. You had quite a mentorship kind of teacher who said, "Hey, there's this international young physicist tournament. Would you be interested in working on this? Mind you, it's going to be like every day in the night, on weekends, things like that, because you're going to work like a scientist, right? Find some kind of hypothetical problem that needs to be addressed, and then you have to research it and write a report, which is like a report, a paper is like a sales tool. You got to convince others that it's real and it's foundational enough, unique enough for people to pay attention to. So that was an early signal that you had a research bent. You really enjoyed kind of pursuing this with your mentor, but also with fellow students who were like in mind. And that was kind of an instigation to continue this journey. And then you realize though that with electronics, and you're playing with transistors and things like that. But you know what? That's such a mature industry right now. You're still relatively young, so semiconductors are already out there and CMOS circuits, and you're thinking, gee, it's so big and yet already pretty mature. And physics is really interesting and it's big, but there's a new idea about quantum physics and maybe even quantum computing in some sense, right? So that kind of sort of gets you into looking at an area that's small, but not huge, that's small enough that you can make your mark, that you can choose some new interesting problems because it's still on the frontier. So you pursue this area when you're in your master's degree, but it as an engineering component, so the practicality aspect of it like your electronics interest, of course, would help from prior to that, and then you get into a physics program, and you had the fortune of reading some of the papers that, what about happens with these quantum particles? Maybe we can make some use of it, whether it's, photonic or neutral atoms or ions or et cetera, or superconducting electrical, Josephson junctions or whatever kind of quantum computing. And you happen to be mentored by somebody as your supervisor for your PhD that had a similar interest, was notable, and it was within a department area founded by a gentleman who just won the Nobel Prize for his foundational work, right? So you end up then getting a PhD in quantum physics, which involves electronics and superconducting circuits and things like that. And then, you co-authored this paper in Nature, right, on the exponential suppression of bit flips in a qubit
Nature physics, yeah.
coded in an accelerator. So that's kind of like noise-based problems, right? And or the cat bit qubit paradigm, which at the time was more of a curiosity back in pre-2019 and when your paper appeared. But then, of course, in the fall of 2019, or later in 2019, you get Google with their claim of supremacy with Sycamore. And it's a toy problem. It's not practical. It's very esoteric. Some controversy. It's hard to verify. And then this whole question then comes of this noisy intermediate scale quantum computing. No, really hard to get practical use because it decoheres and you can't really get it to do things, and that's a big problem. And your work is based on noise biased cat qubits, right? And then that incentivizes you to create this company called Alice and Bob with Raphael to industrialize cat qubit-based error-corrected quantum computing. And of course, that's the big keyword now. Error correction, logical qubits to fault tolerance. And fault tolerance means we can use it for something real, right? And in fact, yesterday, Google just announced on their Willow, they had an article published in Nature with their Willow chip that, you know what, they now have said we've got verifiable quantum advantage. Quantum advantage means that no classical computer can do it in a reasonable amount of time. I'm thinking they're saying it's something like 13,000 years. It's on nuclear magnetic resonance, so it's kind of practical that can be applied to things like chemistry problems or material science. It's not some random circuit sampling, which you can't apply to anything really, other than maybe quantum sort of this random number generation or something like that. But you really can't apply it to anything, right? Practical. And this is kind of a major announcement yesterday, which then falls in perfect because now they're saying fault tolerance is real, error correction is real. And guess what? You published a paper back in 2019, it's real, and you've got some foundational tech to make this thing work. And that's why you founded a company in 2020 on Alice and Bob to capture this on this industrialize this cat qubit based error corrected quantum computing. So did I kind of capture in summary getting you up to 2020, and then we'll iterate from there?
Yeah, no, that's exactly the journey. And what is really fun is, the difference between insider knowledge and general audience knowledge. Because back in 2019, back then, I mean, in the small academic community that was already thinking about quantum computers, fault tolerance was already everywhere. But on the business side of quantum computing, back then, it was all about noisy intermediate scale quantum system. And so for us, it was pretty obvious that there was room for a new player, a novel angle, and bringing attacking fault tolerance head front. Because the only reason the companies out there back in 2019 The reason why they were focused on NISQ was really because fault tolerance seemed too far down the road, or too complex, or and maybe noisy intermediate scale quantum system could have some use. So that didn't felt like a proper way to build a strategy to us. The way we were thinking about that was really, well, there must be a simpler way. This grand challenge of making, escaping the coherence, making large quantum system remain quantum throughout complex and lengthy computation, must have a simpler answer than just brute forcing your way through huge level of redundancy, and build just colossal system to do tiny tasks. And this is how we started investigating cat qubits and built-in autonomous error correction directly within the qubit. But indeed, when we fundraised our seed round late 2019, early 2020, right before COVID, it was really contrarian. Now, 5 years later, or 6 years later, it's obvious. I mean, every single player out there is all about fault tolerance. But yeah, what a journey already. And I'm really curious to see what's going to happen in the next 4 to 5 years, because now every world's map is firming up. I mean, large-scale, impactful quantum computers are just around the corner. I mean, we're targeting 2030, but that's, when you're building large hardware systems, this is tomorrow. So we're actually already building the facility to host it here in Paris. So yeah, it's quite a journey. It's happening very fast.
Yeah, I can imagine you pitching for seed investment back in 2019. People are going, you're talking 2100, 2050. We don't know if it's real, what the computers that are out there, they can't do anything, they're too noisy. And then people say, well, we're going to try to figure out a way of using noisy ones. And they have, right? There are noisy ones, and there's these narrow little applications and things like that, where now we're starting to get at least matching, and maybe in some instances it'll perform better. But really, ultimately, if your underlying hardware and the design of the hardware is better, you're much better off than layering in all of these circuit codes or quantum low density parity code regimes and things like that. You're trying to get more at the fundamental level, so you're way ahead. And of course, I'm sure when you're now talking to investors, you don't have to convince them that fault tolerance and error correction, and especially if you can do it at the hardware level first, before you start scaling up, it's a much better journey than layering in all of this other redundancy stuff, as you indicated, or code distances, and or then at the time when you started. So your fundamental paper, that must be getting citations, right? That exponential suppression of bit flips in a qubit encoded in an oscillator, right? And that's the cat qubit. So I want to get into a little bit more detail about the cat qubit and how it works and why it's named a cat qubit. And then we'll kind of successfully go into
Yep.
all of the great breakthroughs and developments you've done, so that you'll have a scalable, fault-tolerant system that can work enterprise. It'll be a part of every data center. You're going to have a supercomputer. You're not going to get rid of them. You're going to have AI as well. And then you're going to have this hybrid system with quantum in the center, co-locating. But to do that, you need a fairly stable piece of machinery, and that's where you're heading towards, right? Either on premise or in the cloud. Okay, so I've got an audience. Some of them, most of them aren't physicists. They're computer scientists or engineers. So quantum is kind of still new to them, though I should indicate with IEEE, I'm part of them. We've had IEEE Quantum Week since 2020. I've helped them with that. And with ACM, we're finding that our tech talks on quantum are getting engineers attending. They're not interested because they think, I can actually work with this thing now, right? So, but there's a lot out there that are still think it's like it's magic and it's not coming, right? So what is a cat qubit? Like, why is it called a cat qubit, right?
Yeah. So first thing that is really important to note is that a cat qubit is just a special kind of superconducting qubit. Meaning from the outside, I mean, except from the branding of the system, you wouldn't be able to distinguish our systems from Google's or IBM's. I mean, where we operate, it's the same kind of chip. We operate in the gigahertz range, just like Wi-Fi or 5G, for example. We do so on printed circuits that are cooled down at very low temperature, about 10 millikelvin. The thing that is different compared to the standard superconducting qubit it's the layout and what do we print actually on the chip? How do we assemble basic components, capacitors, inductors, to build a circuit, and obviously the maths that govern it. So I don't know how to do the short answer to that is really we designed a quantum bit in a very different way from our competitors. Our competitors are trying a fairly reasonable approach, which is to say, I'm going to go with the most elementary, the simplest possible building block. Just one capacitor, one junction. It really can't get any simpler than that. You can't remove anything from this. And that is the qubit that is called the transmon, the standard qubit that everyone uses in superconducting circuits, or the default approach. And that is a fairly reasonable choice until you realize that for error correction to work, the level of performances, the numbers, actually, when you run the numbers, they are just too hard to meet with that approach. And eventually, the type of orders of magnitude you would need is about 1,000 to 1 overhead ratio from physical to logical. Meaning, if your application, whatever you want to do, simulate a molecule, requires, say, 100 logical qubits, you're going to need 100,000 physical qubits in your system. And that's just tremendously complex and expensive with today's technology. So the thing we did is, get inspiration from other fields, and especially the science of classical automation. The way you design, mechanical subsystem to be stable by design. There is a whole field of applied maths on how do you engineer the equation of motion of a classical system to be stable by design. And so we translated this science into quantum physics. And actually, I say us, it's our advisors, the physicist generation right before us, early 2010s. I think the first paper is about cat qubit as a theoretical proposal is back in 2013 or 2014, something like that. And so the idea here is to say, okay, we're going to engineer a quantum system so that it has two stable states. One we're going to call 0, one we're going to call 1, so that you have a bit. But in a way such that we continuously exchange energy with it to replenish it, because, every system has losses, so you need to re-inject energy at some point. We are also going to extract entropy, cool it down, correct for errors. When you want to correct for errors, you're stabilizing a system, you're cooling it down, you're extracting entropy. But we must find a way to do so without extracting information. Because this is what quantum mechanics is about. It's about keeping the Schrödinger cat box thought experiment sealed so that no information is leaking into the outside world. And that is really the prowess of cat qubits, is to find a solution to that set of constraints. And so eventually, what it leads to, it's a fairly simple system. A system that is just, a resonator on chips, a capacitor, an inductor, an LC resonator, as we call it as engineers, that is coupled to its environment in a very peculiar way, in a way that exchange photons 2 by 2, meaning we're able to dissipate photons 2 by 2 and microwave photons. We're still in the gigahertz, not optical domain, but those are still photons, and inject them 2 by 2. And actually, what is really fun is that when you do the math, it stabilizes the technical word is a subspace of the Hilbert space of dimension 2, so two possible states of same amplitude but opposite phases. So if I go to a standard mechanical analogy, just like a pendulum, physicists love comparing anything to pendulums. So just like a pendulum, and the two possible states, two oscillations with same amplitude but opposite phase. And the way we inject photons 2 by 2 is by driving that pendulum vertically at twice its frequency. Twice the frequency becomes a square in the equation that becomes 2 by 2 photon exchange. And what is really clever about that is that when you do the maths, you find that this creates a qubit that when you crank up the power of your drive of the number of photons you're sending, the typical time between two bit flip errors, meaning switching from 0 to 1, increases exponentially. And when we started the company, we were saturating at a millisecond, which was already 2 orders of magnitude above state of the art. We're now 5 or 6 years later above an hour, so we're now good to go with that error. But that is really the idea of the cat qubits. It's a system that is continuously driven, continuously stable, and that has a built-in error correction for one of the two types of errors, meaning bit flips. And we still need to correct phase flip through redundancy, but that's, and I'm gonna tell you afterwards, gonna be extremely easy compared to when you need to correct both errors at the same time. So that's really the fundamentals of a cat qubit. I encourage your listener to have a look at our white paper on our website, alice-bob.com, in resources, where you'll find the whole philosophy and the quest and the thinking that led to the cat qubit. And maybe for the very technical part of your audience, there is actually an analogy in classical computers to what we're doing compared to the competition, which is the difference between static RAM and dynamic RAM. Your dynamic RAM is that of RAM bars. It's very cheap, just capacitors actively refreshed through active error correction in some sense. But the one that is within your processor is the dynamic RAM. It's the static one, sorry. And it's slightly more complex, but it's always powered, always stable, and meant for compute. So you can also do that kind of mapping in the equations as well. So yeah, that's for a quick intro to cat qubits.
Yeah, and I guess the word cat is really a kind of an homage to Schrodinger and the
Oh,
cat, right?
sorry, I forgot to explain that part. So indeed, no, actually, it's the formal name of the state where we're encoding information into. Its physics name is really a Schrodinger cat state because it's the coherent superposition of two almost classical states. So those those well-defined amplitude and phase type of quantum states are called coherent states, and they're almost classical. And so the cat qubit encodes information in superposition of such states. So it's its formal name. And so we went with it all the way into the logo of the company now, which is a cat, because that was too good not to be leveraged.
There's these concepts of T1 and T2, right? Or this
Yeah.
idea of the system kind of losing energy and it destabilizes, and the other one being the noise susceptibility. Can you give an idea of what the baseline is out there in the marketplace compared to you and how your T1 and T2 is better?
Yep. So actually, we're not better on both. And that's going to be the very interesting part of our approach. So the typical order of magnitude for superconducting qubits is T1 and T2s are, let's say today, on the order of magnitude of 100 microsecond. I think that's a fair order of magnitude for today's state of the art. IBM is slightly better. Other might be slightly worse. But yeah, good order of magnitude. Now, in our case, we're going to talk about T bit flip and T phase flip because there is some subtlety, but we can say T bit flip is T1 and T phase flip is T2. I'm going to get burned by physicists if they hear that, but for the purpose of today's discussion, let's go with that. And so in our case, we're going to have a qubit that is what we call extremely biased, meaning it has a lot of one error and extremely few of the other. In our case, the T1 would be on the order of an hour, while the T2 would rather be on the order of a microsecond or a few microseconds at most. And the whole, you have other physical system that exhibits this property of having very different T1 and T2s. But what is absolutely wonderful with CAD qubits is that we came up with a way to do universal quantum computing with bias preserving gates, meaning we find a way to manipulate information in such that the phase flip errors do not transfer into bit flips and vice versa, so that we can really leverage this asymmetry of errors channel throughout the whole computation. And so the only thing we need to do, and this is exactly what we're doing currently, is actively correcting the remaining phase flip through redundancy. But when you run the number, eventually you end up requiring much, much less redundancy than standard approaches. Typically, compared to the standard approach, we require asymptotically 200 times fewer quantum bits than competing approaches. Meaning not only the machine is 200 times simpler, more reasonable, or you can build it earlier, but it's directly 200 times cheaper. And that's what is providing us a real edge. And this is exactly the momentum we're building on at the moment.
Okay, so let me, if I can summarize this in kind of more layman's terms, and we're not going to worry that it's correct according to physics, right? But in a way that it serves like an analogy in our mind. So let's say if I'm hearing you right, you've got this new kind of exponential suppression on bit flips and this qubit encoded within this oscillator. And the reason you call it an oscillator is because really it can manage the kind of inject energy into the system, so it doesn't, from the energy standpoint, doesn't get into kind of chaos. And the other thing too is there's entropy, this idea of randomness and things like that, right? You're suppressing that tendency as well, and thereby, in this sort of enclosed reinforcing system, you're creating stability that is just not possible using any other technique. Now what happens is, because you've got this more stable system, and you indicated you got this biased, nose biased qubit. In other words, you're able to manage this bit flip in a better way. And you also have a solution on the phase kind of disruptions that occur as well. The combination of the two create a much, much more stable system at that sort of fundamental hardware level. Now what happens is there's surface codes. So in the marketplace now, there's these techniques that come from the idea, the concept comes from classical computing, where you have you can manage what they call parity, or sort of like a sample of what's happening, and then with extra bits correct for that parity. In other words, something happens, you can detect it, and you can correct for it. And then with qubits, what they do is they have these error correction systems called surface codes, and really it's this quantum low density parity checking system where you get other ancillary or extra helper qubits that kind of constantly check without losing information what's happening in the kind of like the data bits, and can make sure that information isn't lost, right?
Yep.
The problem is, and you indicated, is you need like 1,000 of those for every logical qubit. A logical qubit is kind of like metaphor of something that's more stable, and you can do something real with it, right? And so you need all of these helper bits, qubits, to do that. You're saying because you're fundamentally are more stable, you don't need that 1,000 to 1 kind of system. In other words, if you in the existing systems today, if we were to scale this up to, let's say, 1,000 logical qubits, a logical qubit being something you can work with, you can solve real problems with. You're going to need 1,000,000 physical qubits to act as error correctors and helpers to make those logical qubits stable enough so you can do something, which means all of the connectivity for all of that, the couplers, the C couplers and long distance or other longer kind of couplers, the cabinets to house it, the refrigeration to house it. The complexity is unfathomable, right? And you're saying you're able to compress this down like 200,000 times because you've got
200,
a better
200.
fundamental system.
Yeah, that's exactly it. Meaning, when you look at the forecast for quantum computers, when they talk about 1,000,000 qubit, what you must hear is that out of that million, 99.97% are only here for error correction. So this is just how big of a deal quantum error correction is on the path to impactful quantum computers. Thanks to our saving, we're now with our approach at a few percent, I think nearly 6% of useful qubits, so only 94% of overhead. There is still room for improvement, but that's already a 200-fold improvement. And that's really what the community is now realizing as the major hurdle. Because when we look at application and early impactful, broad families of use cases, what we see now is a very clear threshold of utility of quantum computers. I mean, academia has sorted that out extremely clearly. The threshold is 100 logical qubit with a remaining error rate below 10 to the minus 6, meaning below 1 error per million operation. And so now every vendor has that target on their roadmap. The main difference between different modalities is how expensive that system is going to be. And so how economically viable you're going to get at the end. And this is where we have a massive card to play. Because for us, such a system on our roadmap is called Graphene. It's arriving in 2030, and it would fit within today's enabling technology. With fewer than 2,000 cat qubits, we can make that system. And so we can fit that in today's fridges, with a reasonable amount of cables, with a reasonable amount of control electronics. And this is how we've been so capital efficient so far, because we've only raised 130 million so far, and yet we're competing shoulder to shoulder with some of the leading players out there. So yeah, it has roots deep into the maths of what it means to build a quantum computer, but eventually it's an economic advantage for us. This is how you should think of it, in my opinion.
Yeah. So the kind of the current paradigm, and you're seeing a lot of timelines for 2029, 2030 is you need hundreds of thousands, if not 1,000,000 physical of these things to help to create 100 logical. And there's an agreement. You have 100, you can do useful work.
Yeah.
Useful work that's better than what a classical can do.
Yeah, the
And
type of useful work you can do is really around material science or deep physics, condensed matter physics, typically.
yeah, and then what you're saying is that with 2,000 of your physical cat qubits, you can achieve the same kind of 100, and that's a significant difference from hundreds of thousands to, let's say, million to um, um, 2,000. I mean, that's a significant improvement, right? It also makes manufacture easy. And then what will happen is once you start scaling amongst beyond the 100 logical qubits to get more enterprise scale, where you get into the 100,000 and 1,000,000 logical, yours much more easily scales. And this is currently, not to mention all of the discoveries you're going to create in the subsequent years that are coming, right? So I'm just going to quickly outline some of the major areas, and then we'll focus on what this big announcement coming up. So what I'm discovering is, you formed this company in 2020, industrializing cat qubits. And so we get this idea it's much more stable, it's better. May 2020, you get the seed round of about 3 million euros. create a scientific board, and in 2021, your first headquarters in Paris, and with about 32, and you got this 32 first cat qubit chip, the Boson 1 cold tested. In 2022, you got a 100-second bit flip stability milestone on your A and B chip. You get Series A at about 27 million euros, and you got a long-lived bit flip result as a result, documented in a paper, an archive paper. And then in 2023, the theory lives up to 60 times fewer qubits needed for Shor class workloads. And for the audience, the Shor algorithm is really famous still at MIT. It's this idea that you can get a quantum computer to break encryption, and it's the Shor algorithm working on a quantum that can do that. But currently, the hardware is not there to be able to do it. But now people thinking, well, because of things like Alice and Bob, it's going to start coming, right? So in 2023, later in the year, you do a US expansion to Boston, cloud notebooks with partners like Equinix, which is quite a big deal because they're really a big partner. And in 2024, you do error correction architecture advancement, and that's the 200 times fewer qubits versus mainstream stacks. 200. So I think earlier I was saying 200,000, but 200 times. But could be 2 years, you'll hit the 200,000, right? So
we're getting there. We're getting there.
and then in 2025, you raise a Series B at 100 million euros to accelerate the roadmap for use of quantum by 2030. And you actually have now banks invested in you, right? It's like a BPI France, for example.
Yeah.
Which is because, by the way, I see two other big areas for quantum, and that's in healthcare, but also in finance. A lot of investment coming from finance, right? And then in May 2025, a new 50 million round, a 4,000 square meter Paris product development lab. So now you can build this stuff with quantum machines on the control side, and they're famous in that area. You got Blue Forest for the cryogenics. So you got the refrigeration stuff handled. The facility is planned to host 200 dilution refrigerators, a nano clean room for rapid prototyping, Q2. And then in June 2025, you're selected to be the French Next 40, first quantum computing firm in the program, which means that's a bet by the government and the industry around you. September 4, 2025, AMB and RIA collaboration for more efficient magic state preparation. So just to kind of a little bit of background, when you have quantum, you have this kind of Clifford states, which are easy. And then you have these things called T-gates, which is more complex. It involves this kind of phase or this quarter turn, right? Which is much harder to do, is much more complex. And magic states is the way to do this more easily, right?
Yeah.
In a sense. And so you got magic state preparation, more efficient, and not just magic state, but more efficient magic state preparation, because in quantum computing, you need Clifford states, but you need this kind of T-gate kind of capability to do fault tolerance. And you've even improved on that. And September 16th, you're hiring plan to 100 more people by mid-2026. And we only have a few minutes left because I know you have to go. But now you got this massive announcement, more major breakthroughs. And this interview will not be released until after October 28th. So we'll hold it when you do the public release. So go ahead.
I mean, it just, it's the logical follow-up on the story you just said. We're ramping up our capacity, scaling towards, large-scale commercial impact. We made some tremendous progress on the hardware side, but we still need to think and build all the middleware and software environment for application to be developed. And so this is where we have the chance of partnering with NVIDIA, and this is what this is about, is we're extremely happy to contribute to NVQ Links, an NVIDIA initiative to unify the vision around the middleware of quantum computing. And what does it mean to program and all those layers of abstraction? Because the way people program quantum computers today is at such a low level. It has no classical analogy. It's connecting bits directly one by one together. I mean, no language lets you do that. It's at such a low level. So you need abstraction layers to include first error correction, then manipulate logical qubits and manipulate registers, then have some libraries of subroutines and things like that. And you need to coordinate that whole stack in a very clever way. And so the way we're contributing, helping out on this global effort to create those standards is through this partnership with NVIDIA, where we're really contributing from a hardware point of view to make sure this framework and languages are well aware of the specificities of each platform to make the most of the available hardware at the end of the day, and make sure that huge community that will emerge around the quantum economy and applications has the right tool and the best access, the best environment to code their application. And so it's really, I think, the announcement in itself, it's just the follow-up on the story. But when you zoom out, I think what is currently happening is a proper tipping point on the industry. We're no longer discussing the fundamental of physics. We're no longer about the specificities of each individual qubit. We're now all moving from basic science to engineering scale up at that point. And so in that phase, we're starting to build the whole stack, the whole layer of applications on top of that. And you mentioned earlier the growing involvement of engineers through IEEE, for example. And I think this is really what is currently happening. And so now it's not only the hardware electronics engineer contributing to quantum computing, it's also the whole software community bringing the knowledge of how do you build compilers, how do you build abstraction layers for that whole new paradigm. And there is so much to be done. We're glad to participate with NVIDIA in that.
Yeah, I mean, I'm on being on the board committees and chairing in ACM. We're number one in computing science. We have the best conferences, journals, and things like that in that area. And I'm involved in the committees, the board committees on Tech Talks, and I actually chair the one on Bytecast. And we've been finding on the Tech Talks that they're our most popular sessions now, and that's because half of our audience are actually software engineers. And so they're like you said, the missing link for many years was the full stack. There's this esoteric, or what appears to be esoteric to many people, quantum computing. What are the meta layers? What are the kind of the abstraction layers? So I don't have to deal with the phases and the X, Y's, and Z's and all of this kind of stuff, which software developers don't want to get into, right? How can I really work with Python libraries and other kind of software tools that will do the translation for us? And now, NVIDIA has Q2Q, which act as a bit of a orchestrator with hybrid and simulation, and also determining where to place the niche jobs into a quantum processor. And you're saying now you're part of, in a fundamental way, of NVQ Link, which is an open architecture. Open means they're not trying to hide anything. They want everybody to embrace it. Quantum processing units with graphical processing units for real-time, low latency control of fault-tolerant computing, right? So enables GPU-based live error coding, decoding, I should say, and dynamic collaboration across qubit types. Tasks once confirmed to or confined to custom hardware. What you're doing is you're integrated into that to bring logical qubits and industrial grade fault tolerance quantum computing closer to everybody, so that anybody can do this. So you're not just have to be a PhD like you is are in physics and working with, Nobel Prize winners like you have on your scientific board. So you're bringing that all into kind of a real time because this effort then builds on the dynamics, Alice and Bob's NVIDIA accelerated simulator integrated with the Q2Q platform. So it builds on dynamics. Alice and Bob's NVIDIA accelerated simulator integrated with the Q2Q platform. So it integrates with that and signals growing maturity for practical, scalable workloads, right? And that's an amazing kind of capability. And I know that in the near term, achieving 6 nines logical qubit, that's 1 error per 10 to the 6 operations. That's in your roadmap already. Completing the first below threshold logical qubit on the helium series, and advanced bias preserving 2 qubit gates and repeated phase flip detection to enable live error correction. And I know that's near term, midterm, delivering graphene and 100 high fidelity logical qubits integrated into computing workflows for useful industry relevant problems and aligning with French national ambitions, and then working towards 128 logical qubits by 2030, and industrial steps beyond and beyond 2030, scaling to larger logical systems, thousands of logical qubits, expanding application domains, materials, pharma, optimization, and finance. That's important. Finance, $160 trillion assets under management. JP Morgan just announced 1.5 trillion in investment they're making, of which quantum is a big part. So why not them investing in you? I'm just kind of brainstorming here. Hardening the full stack from qubit hardware to error-corrected logical operations, which everybody can believe in, integrated into their industrial-grade enterprise-scale operations, and magic state factories for universal quantum computing. And these are statements that Alice and Bob, you're making. Did I say anything that was out of turn? This is what you're doing, right?
I mean, there is a lot happening at Alice and Bob, and really what I love about the current momentum is that we're now, entering the delivery phase. It's no longer about getting the right ideas, and so now we're at a completely new stage, and it's so great for us to, build this new paradigm of compute on the shoulder of giants. And the growing role GPUs and AI is playing in building quantum computer is extremely exciting at the moment. We had a previous partnership with NVIDIA to develop dynamics, the simulation engine, leveraging GPUs to help us design and control qubits in a better way. Now, through this whole NVIDIA ecosystem, we can bring GPUs as a booster to help on some of the workload, whether they're calibration, whether they're quantum error correction, and help, smoothly hybridize. Because the future of computing is not quantum taking over classical computing. It's quantum bringing a whole new classes of problem, of thing you can solve into the mix, and building on top, and bringing a complex and unified mix. Just like GPUs did not replace CPUs, the quantum part will be one new type of booster that needs to be tightly integrated within that ecosystem. And seeing that starting to be built today is extremely exciting. I mean, we're definitely nearing the end of the race. It's closing in, and so really, I think it's going to be a fun few years ahead of us to see how fast we can progress on that road.
I know, Theo, we're actually a little bit above beyond your time, but let me finish with one additional statement, and I'll get you with the one closing statement, and that is, this month the Nobel Prize in Physics went to John Clark, Michel Devoret, and Martinez for their macroscopic quantum effects in superconducting circuits. And and Deborah Ray actually co-invented Alice and Bob's cat Qubit. And Martinez is on your consultative board. So you've got now Nobel Prize winning validation of your science, right? And so you must be thrilled to have that validation, right? And one final statement, and my apologies, I know you have a hard stop at 10 my time, but 7 your time. So one final statement, and we'll close this off. So thank you again for coming in.
Thanks a lot, Stefan. Indeed, it's very exciting, and the Nobel Prize is really just cherry on the cake at that point. But yeah, I'm really thrilled about what the next few years are going to be. A lot of scaling fundamental physics into actual industry reshuffling machines, because that's what quantum is all about. And now that computing is taking such a large place in today's economy, with infrastructure investment in tens, if not hundreds of billions of dollars in computing. It's definitely going to be one hell of a ride for the next decade in quantum. So I'm looking forward for that.
Yeah, and hopefully when you're 10 billion valuation on one of your subsequent rounds, that you'll still do an interview with me.
Surely will. Thanks a lot, Stefan.
Okay, take care. Thanks a lot.
Thank you for listening to the Brand Called You videocast and podcast, a platform that brings you knowledge, experience, and wisdom of hundreds of successful individuals from around the world. Do visit our website www.tbcy.in to watch and listen to the stories of many more individuals. You can also follow us on YouTube, Facebook, Instagram, and Twitter. Just search for the Brand Called You.